Welcome to Making and Treating of Steels course, Lecture 28. I am going to speak about continuous cooling transformation diagrams in this lecture. What does it mean? What is the main purpose of continuous cooling transformation diagrams? There was a limitation of time, temperature transformation diagrams, that is, it is nothing but an isothermal transformation diagram. Isothermal means transformation times are representative and followed by quenching, instantaneous quenching, keeping the temperature constant and instantaneous quenching. But it doesn't talk about what is the cooling rate, how as the temperature is dropping down, how the cooling rate is varying. Cooling rate may be, it is a parameter of temperature by time, dt by dt, temperature, change in temperature by change in time, that is not considered in the TTT diagram, which is addressed in the continuous cooling transformation diagram. Practical situation as per the industry scale, it is playing with the temperature and time scales. This particular cycle of treatment need to be addressed about any of the samples. It could be the forming process, working process and treatment process. These are the two parameters need to be addressed and calculated exactly, because this particular cooling rate, as the temperature is dropping down within the furnace or in the atmosphere at the quenching time, quenching is nothing but cooling time, it may or may not be constant. So you need to consider, which is considered in the continuous cooling transformation diagram. That is, this particular diagrams main consider rate of cooling. The rate of cooling may be slow, just like in the furnace, may be rapid or too fast, just like in the water. So it need to be addressed, that is need to be talk, which is addressed in the CCT diagram, which was not done in the time temperature transformation diagram. Hence, in the practical applications, this TTT curves have the limitation of this cooling rate, where this separate continuous cooling transformation diagrams need to be drawn, since it was not addressed. But drawing the separate transformation diagrams, cooling transformation diagrams, as a continuously cooling was occurring, it is great difficult. Even the cooling curves also is being plotted in one single graph with varying time and temperature, which is addressed in the continuous cooling transformation diagram, where the times, transformation times also represented, microstructures also noted with the continuous cooling treatment. That is, this particular diagram's specification or speciality. This particular diagram mainly gives an idea about the cooling rate, which was the limitation, the change in temperature by change in time. This particular cooling rates, and you no need to draw for the separate diagram for each and every cooling rate. If you take a differential of these things, you can draw for all these particular variety of quenching medias at different temperatures. You can draw one cooling curve. That is done in this CCT diagram. But what is the difference between these continuous cooling transformation and time temperature transformation is that this particular continuous cooling transformation will not emphasize on bayonet transformations. Bayonet is just like ferrite plus cementite, but instead of Fe3C, it is Fe2.4C. That particular thing, bayonet transformation starting and finishing, is not addressed in the continuous cooling transformation, which was done in the time temperature transformation diagram. That is also another phase transformation, heat treatment. These diagrams are very important. Please make a note. This is one of the example of continuous cooling transformation curves for eclectoid steel. This is eclectoid temperature 723. This M stands for martensite, P stands for perlite. These are the various temperatures in degree Celsius. These are the variety of the processes of cooling process. It could be the annealing is nothing but furnace cooling, air cooling, and oil quenching, oil cooling, water quenching, water cooling. These are the standard cooling rates are achieved by experimentally proven table, and this is the time. This is 10 to the power of minus 1. This is 10 to the power of 0. This is 10 to the power of 1. This is time scale in seconds. For example, if you take water quench, the steel, eclectoid steel is heated at that particular 723 temperature, soaked for 1 hour and cooled in water. So temperature drops with this much difference, 600, and this much. This is the cooling rate at 600. At 500, this is the difference of cooling rate. As it is coming to the 100 degree Celsius room temperature, this will be the cooling rate in water. That is why fast cooling rate you are getting in the water quenching. Finally, you will get the product, microstructure product, which gives an idea is martensite. And if you take oil, same steel, if you quench in oil, and this is perlite starting point, this is perlite finish point, there will be some amount of perlite is added along with the martensite. It could be the 10% of perlite, remaining is martensite in the case of oil quenching. If you do air cooling with this particular time interval, perlite starting, perlite finishing, this much amount of perlite, that particular perlite is initially started perlite is at this for this much amount of time, it is fine perlite is formed, which is called normalizing process, one of the heat treatment process, air cooling process. Fine perlite you will see in the microstructure, and full annealing process, and there will be coarse perlite. The perlite structure, perlite grains are grown. The coarse perlite grains you will see. The annealing process is within the furnace cooling. It could be the muffle furnace, it could be the any of this particular electric furnace. Within the furnace, if the cooling is being done just by switching off that particular instrument and bringing down to the room temperature, where you will see at the end microstructure coarse perlite, the cooling rate will be this much. This is how it is varying from the 600, 500 and 100. So this will be the cooling rate. It will take very long time for cooling. And coming to the microstructures, as I was talking about perlite, bayonet and martensite. Bayonet I emphasized in the TTT diagram how this particular microstructure looks. This is perlite. These are called pearls. This white bands are ferrite, and this particular dark band is perlite structure. This is an alternative band of ferrite plus perlite, which looks like pearl shape. That's why it is called perlite structure observed in steel. Bayonet is feathery structure, just like peacock feather tree. The feathery structure you will see in the steels. This was a microstructure taken. Example, the heat treatment around 348 degrees Celsius temperature. This is martensite. Martensite is just like needles. Needles are grown from the boundaries, just like dendrites growing. This is martensite structure. The product microstructures of TTT and CCT diagram you will see perlite and martensite. Now let me introduce another topic called heat treatment process. The initial idea about the TTT and CCT diagrams gives an idea to know more about the heat treatment process. Towards this aim, you need to know about CCT diagram and TTT diagram and microstructure development. What was main the process, how this particular microstructure evolution occurs is understood there. This is a reference textbook for the heat treatment process. Now let me talk about heat treatment of steels. Here I am emphasizing on heat treatment of steels, not non-ferrous materials. As we have noticed that TTT and CCT diagrams helps us in designing the heat treatment process, microstructures such as pearlite, martensite, and bringing suitable engineering application properties. That is why these are useful for heat treatment process, all these things. And this particular heat treatment processes are divided into three different categories. If it is heating and cooling phenomena is called as a thermal treatment or heat treatment. If it is deals with the forces, is called as a mechanical treatment or working treatment. If changing the composition by melting and casting, that is chemical treatment process. Treatments are divided into three different. Example, heat treatment, heating and quenching, mechanical rolling process, chemical melting process. It could be the combination of these things. Thermomechanical treatment process, thermochemical process, just like case carburizing process. That is also another heat treatment process which I am going to discuss in the next lectures. And this particular heat treatment may affect entire sample, which is nothing but bulk of the sample when you do this particular treatment, or it may affect only the surface hardening. Only surface may getting hardened, the bulk core of the sample may retain as it is. And the typical industrial practice is combination. It follows combination of steps, thermochemical, thermomechanical. These are in practice in the typical industry practice. The broad classification of the heat treatment process. What is this particular heat treatment process? How does it is classified with respect to the subject of interest, heat treatment of steels? The heat treatment could be bulk heat treatment and surface heat treatment. If it is bulk heat treatment, broadly classified into annealing, normalizing, tempering and hardening. And surface treatment, thermal treatment and thermochemical treatment. Thermal treatment is induction hardening, surface hardening treatment. Thermochemical treatment, carburizing process. Only carbon is induced at the surface so that the surface is getting hardened. By induction furnace, the induction treatment, thermal treatment, the surface getting hardened. And bulk treatment, annealing process, further classified into fully annealing process. Based on the temperature chosen from the iron and iron carbide diagram, it is called above A1 temperature, which is called full annealing temperature. Below this particular temperature, that is also you are going to see in the annealing process in the next lecture. Recrystallization annealing process, stress relieving, the stresses which are retained from the mechanical working process, it can be relieved by doing annealing process. You can allow, by doing annealing process, you can recrystallize, nucleate and recrystallize, the strength can be improved. And spheroidization, by forming the inclusion spheroidization and grain spheroidization, the strength will be increased for the material. Now give your opinion on this particular topic, that heat treatment of steels, what does it mean? It involves heating and cooling of steel in controlling the time temperature conditions. So this is main aim of heat treatment process. Please give your opinion as true or false.